This question is about the directional derivative, and I'm also going to talk a little bit about the gradient and what these things mean. I'm going to do two problems that are pretty much the same form. They work out a little bit differently. The first one is to find the directional derivative of natural log of x squared plus y squared at this point in this direction. And I'm going to do the same thing for this other function. This is inverse tan, arctan of, this should be, x times y, not x comma y. That's a mistake. So into arctan you're plugging in the product of x, y, and at this point 1 comma 2 in the domain you're going to find the directional derivative in the direction of v, which is 5 in the x direction and 10 in the y direction. Alright, so let's get started with the first problem here. So you need to know or be prepared to rederive the formula for the directional derivative. And so the easiest way to remember it is that it's the dot product of the gradient and direction vector. So this vector that we're given, it has like all vectors, it has a direction and a magnitude. But this vector is not a unit vector because its magnitude is not 1. So to find the directional derivative, it's important that we do use a unit vector. So that means that we have to normalize v. So u is going to be equal to the vector v divided by the norm of v. And my handwriting is not great. So what should these things be? So it's easy to convince yourself that the norm of v is the square root of 5. I take it that's a no-brainer. And so that means v divided by the norm of v is going to be minus 1 over the square root of 5 and 2 over the square root of 5 in this component. Okay, so now we have a direction which is has a unit magnitude, and now we're going to find the gradient. So let me remind you that the gradient of a function is just the partial with respect to x in one component and the partial with respect to y in the other component, and the analogous thing if there's more than one variable. So for this function, this is going to be, what's the partial derivative of this thing with respect to x? Well, I'm going to assume that you can easily deduce that it is 2x over x squared plus y squared. And that's because the derivative of a logarithmic function is 1 over the input, and by the chain rule you need the derivative of the input on top. So similarly, the second component is going to be 2y over x squared plus y squared. Okay. And we want the directional derivative to actually be a number, and we're going to need to evaluate the gradient at the particular point we're given, which is 2 comma 1. So to sort of get things down to reality, we need to plug in 2 comma 1 into this vector function. And what is that going to give? That's going to give 4 here and just 2 here. And now the denominators are going to be the same. What is it going to be? It's going to be 1 plus 4 is 5. Okay. So now we are ready to finish up. So the directional derivative in the direction of u of f is the dot product of this vector, which is the gradient evaluated at the point, and the normalized direction vector, which is this. Okay, so we just take the dot product as usual. That means this times this. That gives you minus 4 over 5 to the 3/2 power, plus this times this is 4 over 5 to the 3/2 power, and this is equal to 0. So that means that the indicated direction is right along a contour line. And I've made some visualizations for understanding what's happening here. I think the easiest way to understand the directional derivative is in terms of temperature. So what this means is if you walk in this direction, the temperature doesn't change. Can you just think for a second and understand how that would be true? If you have two input variables, x and y, and they give location and the output is temp, then if you move if the directional derivative with respect to temperature is 0 in a certain direction, that means the temperature doesn't change in that direction. So I've translated all this into Sage so we can get a visualization of what's happening. You can see here's the function. And I've also made a 3D plot of that function using Google. You can see that it looks kind of like a black hole. So this is the function natural log x squared plus y squared. All right. And so we're going in a certain direction, and what's going to be the case is that the direction that we've chosen is exactly along a level curve of the black hole. So you're sort of walking along the rim. So let's see more why that's true by going through the Sage stuff. And I'm going to run through what I've done here in Sage really briefly, but it's not really essential. This is the given point, 2, 1. This is a plot of it. This is the contour plot of the function that I'm going to use. And just for some things that I'm going to do with the plotting, I need a vector for the origin. And this is the direction vector. Remember, the given direction is -1, 2. And we need to normalize that so that it becomes a unit vector. So now dir is the unit version of the given direction. So we need the gradient of f, and I evaluate gradient at the given point, and notice that that's exactly what we got when we computed it by hand. And now let's put all these things together in a picture. And okay, so what have we got here? So this is a contour plot of the function that's looking straight down the black hole. So something like this, okay. So we're looking straight down the black hole, and then we've also got 3 other features here. One of them is the point of interest. This red dot is just the point of interest, 2, 1. And blue here is the arrow or the vector that goes from the origin in the given direction. So this blue vector is the unit direction that we're given. And you can see that it is right along this contour, right? We're walking right along this contour, which is a level curve where the values of f don't change. Now, this orange arrow is the direction of the gradient, which means the direction of steepest increase. And you can see that it's true in this function, right? It's telling you that the direction of steepest increase is right away from the center of the black hole, which is clearly true. And note also that the direction of the gradient is orthogonal to the direction of the contour line, and that's always true. So these things are at right angles. The directional derivative is basically their dot product, and since they're orthogonal, their dot product is 0. So that's several ways of understanding what just happened. Then we can translate those things over to the point and get a slightly different point of view on the same thing. So here we go, like this, right? Okay, so we have the other example to go through. So let's scroll down here. So it says find the directional derivative of the given function in the given direction. So this time we're working with arctangent, and the point is just is 1, 2, and this is the direction. Now it's given in this notation instead of the component notation. So let's normalize v. So what is the norm of v? V norm is equal to the square root of, actually, you know, it's going to be more convenient. Can I just do this? W is equal to 1, 2. So I hope that's not confusing. It's just easier to work with these numbers. It's going to end up being sort of the same thing. So this goes in the same direction as that, except that the numbers are a little bit easier to work with. I shouldn't do that, should I? I've already opened my mouth, so let me erase this. We'll just do the problem as it's given, but that would be a good idea if you were just doing it instead of trying to explain it. So what is the norm of this thing going to be? It's going to be 25 plus 100. So it's the square root of 125. Okay, and so that's 5 cubed, isn't it? So this is 5 to the 3 halves. Right? And So what is u is going to be v normalized. So that is going to be, in component notation, 5 divided by 5 to the 3 halves, and 10 divided by 5 to the 3 halves. So now we have our unit direction, and we need to write down the gradient. So grad f is going to be, so the normal derivative of arctan is 1 over 1 plus x squared, so just putting that in this situation together with the chain rule, you can see that you're going to get y here over 1 plus xy squared, and similarly you're going to get x over 1 plus xy squared here. And I seem to have a problem with wanting to write a comma for no reason. Alright, and we want to plug the point of interest in here. So in this problem, the point of interest is 1, 2. So let's plug 1, 2 into the gradient. And what is that going to do? We're going to get 2 over 5. And this is going to be 1 over 5. Okay, so now let's take the dot product of this thing and the unit direction. That's going to be the final answer. So it's going to be the dot product of 2 over 5, 1 over 5 dot this, the unit direction, is 5 over 5 to the 3 halves, comma 10 over 5 to the 3 halves. So just computing the dot product as we normally do, this is going to be 2 over 5 to the 3 halves plus 2 over 5 to the 3 halves, which is equal to 4 over 5 to the 3 halves. And if you do this on a calculator, which I guess I did right here, you can see it. Actually, you can't, but here it is. Right there, see? So that turns out to be the number 0.3577. And then some other stuff, but that's close enough. Okay, so that means that if you're in, you're standing on a plane and there's temperature where you're standing, if you walk in this direction, then temperature increases at a rate of 0.3577 degrees per foot, or whatever unit you're using to represent direction and the magnitude of direction in the plane. So let's go through the SAGE. So I did pretty much exactly the same thing here. So now f is arctangent and the point of interest is 1, 2. Make a contour plot, make the origin. Here's the given direction, and we normalize it. Now I also added something else here. You can see, I'll get to that when I come to it. So I also have the vector projection of the gradient onto the unit direction. And I did that because it means something about the magnitude of the directional. I guess the directional derivative is a magnitude, but it means something about the directional derivative. So here are all these things in a plot. This is the point of interest, and the blue line, like before, is the unit direction that we're interested in, and like before, the orange vector is the gradient, and this green vector now is the projection of the gradient onto the direction. You can see that is what's happening here, right? And the reason I did that is because one way to understand what the directional derivative is the directional derivative is the scalar projection of the gradient onto the unit direction. In other words, the directional derivative is the magnitude of the green arrow. So you're at this point, and the directional derivative in the blue direction is the magnitude of the green arrow, which is the scalar projection of the gradient onto the given direction. So just for fun, here's the 3D plot of tangent. and that's pretty much it. That's pretty much it. Did I do? Yeah, now we just can translate the picture over to the point. And that's all. So it's pretty simple. Let me stop the